A telescope in Chile just turned the night sky into something closer to a movie than a photograph. And what it caught in its first 10 hours of testing is still being unpacked by astronomers. No invented signals here, no fabricated warnings, just real numbers that are genuinely hard to wrap your head around. Let's start with the machine itself, because the scale involved here is almost absurd. The Vera C Rubin Observatory sits on Cerro Pachón, a mountain in Chile chosen for its dry air and dark skies. At its core is a camera roughly the size of a small car, weighing around 3,000 kilograms, and capturing images at 3,200 megapixels. To put that in perspective, displaying a single one of Rubin's full-resolution images at true detail would require hundreds of ultra-high-definition television screens arranged together. That's one image. But raw resolution isn't actually the point. Plenty of instruments can take a single, extremely detailed photograph. What makes Rubin fundamentally different is what it's built to do with that camera. Rubin's mission, called the Legacy Survey of Space and Time, involves scanning the entire visible southern sky repeatedly, roughly every few nights, then comparing each new image against everything captured before it. The goal isn't a perfect photograph, it's catching what's different. On June 23, 2025, Rubin released its first test images to the public, built from just 10 hours of preliminary observations, before its full 10-year survey had even officially begun. One of those first images became an instant sensation. A single field of view, built from 1,185 individual exposures stitched together over just 7 nights of observing, contained an estimated 10 million galaxies. Scattered among those distant galaxies were much closer objects too. Stars from our own Milky Way, their light spreading into sharp diffraction spikes caused by the telescope's own internal optics interacting with their brightness. In a single frame, you're looking at objects in our galactic backyard and galaxies whose light traveled for over 1 billion years to reach us, all layered together in one continuous view. And here's the part that genuinely stunned astronomers when they realized it. Building an image this large, this deep, covering this much sky, would have taken older space telescopes an absurd amount of observing time to reproduce. Rubin did it in 7 nights. One of the most detailed early scenes came from the southern part of the Virgo cluster, the nearest large gathering of galaxies to our own Milky Way, sitting roughly 55 million light-years away. In that single field, Rubin captured an enormous range of galactic activity happening simultaneously. Some galaxies glowed with bright blue light, the signature of young, hot stars actively forming inside their spiral arms right now. Others showed softer yellow and red tones, evidence of much older stellar populations in galaxies that stopped forming new stars long ago. The image included Messier 49, a giant elliptical galaxy packed with ancient stars and wrapped in a soft golden glow. Sitting near NGC 4535, a face-on spiral actively lit up with fresh star formation and bright blue-white arms. Further back in the same frame sat dwarf galaxies, massive ellipticals, delicate spirals, and faint reddish smudges representing galaxies more than 1 billion light-years away, barely visible as tiny points of light scattered across the black. And then there was one of the most dramatic features in the entire field. A triple galaxy merger, 3 galaxies actively caught in the process of colliding and reshaping each other through gravity, their structures torn, stretched, and twisted into long tails and bridges of stars. That's not a peaceful, static sky. It's a genuine snapshot of ongoing cosmic violence, 3 galaxies actively merging into something new, caught mid-transformation. That's exactly what makes Rubin's first images so different from a typical astronomical photograph. They're not static portraits of a fixed universe. They're frozen moments pulled from a sky that's constantly colliding, forming, aging, and transforming, whether or not anyone happens to be watching at that exact moment. There's another detail buried in these early images that's genuinely worth appreciating because it shows Rubin doing exactly what it was built for, almost by accident. While staring deep into distant galaxies, Rubin's long exposures also caught our own solar system cutting directly across the frame. Thin, colored streaks appeared scattered among the galaxies, the trails left behind by asteroids moving during the exposure. These weren't errors or glitches. They were real solar system objects, quietly crossing through one of the deepest test images ever taken. Rubin's processing software is specifically built to recognize these streaks, remove them from the final combined image to keep the deep sky background clean, while simultaneously flagging every one of them separately for cataloging and discovery. And the numbers here are where things get genuinely remarkable. In roughly 10 hours of test observations, Rubin detected 2,104 previously unknown asteroids. For comparison, every other ground and space-based telescope on Earth combined typically discovers around 20,000 new asteroids across an entire year. Rubin found roughly a tenth of that total in a single night of preliminary testing. Astronomers currently know of roughly 1 million asteroids across the solar system. Based on Rubin's early results, researchers now expect that total to climb towards several million within just the first couple of years of the observatory's full operation. That's not a minor improvement to asteroid tracking. That's a fundamentally different scale of discovery, happening almost as a side effect of a telescope built primarily to study galaxies billions of light years away. People naturally ask how Rubin compares to telescopes like Hubble or James Webb, and the honest answer isn't that Rubin is simply better. It's built for something genuinely different. Hubble and Webb are exceptional at deep, targeted observation, zooming in with incredible precision on a single galaxy or nebula to reveal fine structural detail. Rubin's job is almost the opposite. Instead of a narrow, deep look at one target, it's built to turn the entire visible sky into something closer to a continuous film. For most of the history of astronomy, the field has largely relied on still images, single snapshots capturing one particular moment in cosmic time. Rubin changes that fundamentally by scanning the same regions of sky repeatedly. That process subtracts out everything that stayed the same between observations, isolating only what actually changed. A star that suddenly brightened, a supernova that appeared where nothing was visible before, an asteroid that moved, a distant black hole flaring briefly before fading again. A variable star pulsing on a predictable cycle. Once Rubin's full survey is fully underway, the observatory is expected to flag potentially millions of changing objects across the sky every single night, each one becoming a small alert that astronomers anywhere in the world can investigate. That capability comes with a genuinely staggering amount of data. Rubin is expected to generate roughly 20 terabytes of raw information every single night it operates. Across its planned 10-year mission, that adds up to tens of petabytes of data and millions of individual exposures. An amount of information so large that processing it requires dedicated data pipelines built specifically to keep pace with what the telescope captures each night. Beyond galaxies and asteroids, Rubin's early images also turn toward one of the most visually striking processes in astronomy, active star formation. In another early release, Rubin captured detailed views of the Lagoon Nebula and the Trifid Nebula, two of the most well-known stellar nurseries in our own galaxy. But rather than showing them as simple, isolated, glowing clouds, Rubin's wide field of view placed them within their broader surrounding environment. The Lagoon Nebula, roughly 4,000 light-years away, appeared as a vast cloud of glowing pink ionized gas, packed with newly formed stars already reshaping the very cloud that created them. Nearby, the Trifid Nebula combined glowing emission, soft blue reflected light, and dark lanes of dust into one striking layered scene. Both nebulae had already been photographed beautifully by earlier telescopes. What Rubin added wasn't necessarily sharper close-up detail, but scale and context, showing these stellar nurseries not as isolated, disconnected objects, but as part of a much larger, more active surrounding region of the galaxy. And because Rubin will return to these same regions repeatedly over its 10-year survey, astronomers won't just have a single snapshot of these nebulae. They'll be able to track how they actually change over time, watching newly formed stars brighten. Variable stars flicker on their own cycles, and the surrounding gas and dust shift as star formation continues to unfold. Here's the honest, important context to hold on to through all of this. What made these first images genuinely significant to astronomers wasn't that they represented some kind of alarming discovery. It's that they proved the machine works exactly as intended at a scale that's difficult to fully process. The galaxies, the merging trio, the asteroid trails, the glowing nebulae, all of it served as confirmation that Rubin's instruments, software, and data pipeline could actually deliver on the observatory's core promise before its official 10-year survey had even formally begun. The real transformation starts once repetition enters the picture across the full survey. Once Rubin begins systematically revisiting the same patches of sky, night after night for a full decade, the universe stops looking like a fixed static backdrop and starts revealing itself as something constantly in motion. Supernova will be caught early in their brightening phase, rather than after the fact. Variable stars will have their pulsing cycles tracked with unprecedented consistency. Black holes will have their occasional flares recorded as they happen. Asteroids will be tracked drifting through the solar system in numbers previous surveys simply couldn't match. And entirely new transient events, phenomena nobody has specifically predicted or cataloged yet, are expected to show up simply because, for the first time, an instrument exists that's actually watching closely and consistently enough to catch them. That's genuinely what separates Rubin from every major telescope that came before it. It's not attempting to replace Hubble or James Webb, and it doesn't need to. It's tackling a problem neither of those telescopes was ever designed to solve. Not what a single galaxy looks like in extraordinary detail, but how the entire visible sky actually behaves and changes night after night across an entire decade of continuous observation. So here's where things stand today. Rubin has successfully completed its initial testing phase, and its first public images already demonstrated a genuinely staggering scale of capability. 10 million galaxies in a single frame, over 2,000 new asteroids found in a single test night, and detailed views of active star formation happening in real time within our own galaxy. The full legacy survey of space and time is now getting properly underway, expected to run for a full decade, systematically scanning the entire visible southern sky over and over, building toward a genuinely unprecedented, continuously updated record of how the universe actually behaves, rather than a single frozen picture of how it happened to look in one specific moment. That's the real story behind Rubin's first images. Not a warning and not evidence that anything about the universe has suddenly become dangerous. Simply proof that humanity has, for the first time, built an instrument capable of watching the sky closely enough and repeatedly enough to finally notice everything that's actually been happening all along. One of the biggest scientific goals behind Rubin's decade-long mission reaches far beyond beautiful photographs or even asteroid discoveries. At its heart, the observatory was built to help answer two questions that have challenged astronomy for generations. What exactly is dark matter, and why is the universe expanding faster over time instead of slowing down under its own gravity? Those two mysteries account for roughly 95% of the cosmos. Yet scientists still don't know what either one physically is. Rubin cannot photograph dark matter directly because dark matter doesn't emit, absorb, or reflect light. Instead, the observatory measures its influence through gravity, watching how millions of galaxies bend, stretch, and subtly distort the light from even more distant galaxies behind them. This effect, known as weak gravitational lensing, is incredibly small for any individual galaxy. But when measured across billions of galaxies, those tiny distortions reveal enormous invisible structures stretching across the universe. It's similar to watching leaves floating down a river. You may not see the current itself, but by carefully observing how every leaf moves, you can map the flow beneath the surface. Rubin will perform that kind of measurement on an unprecedented scale, collecting enough observations to build one of the most detailed maps of dark matter ever attempted. The observatory will also help scientists investigate dark energy, the mysterious phenomenon causing the expansion of the universe to accelerate rather than slow down. By tracking the positions of galaxies over billions of light years and comparing how cosmic structures evolved throughout history, researchers hope to place tighter limits on competing theories explaining this unexpected acceleration. Whether dark energy represents an unknown form of energy, a property of empty space itself, or evidence that gravity behaves differently across enormous distances, remains one of modern physics' biggest unanswered questions. Rubin won't answer that mystery overnight. But over 10 years, its observations could significantly narrow the possibilities by providing a dataset, unlike anything astronomers have ever collected before. The observatory also has an important role much closer to home. Planetary defense agencies around the world are particularly interested in Rubin's ability to discover previously unknown near-Earth asteroids. Most asteroids pose absolutely no danger, and the overwhelming majority remain safely distant from our planet. Even so, identifying their orbits years or decades before any potential close approach gives scientists valuable time to calculate future trajectories accurately. Rubin's wide field of view allows it to scan enormous sections of the sky rapidly, increasing the chances of finding faint objects that earlier surveys might have missed entirely. Every newly discovered asteroid improves our understanding of the solar system's population and helps refine long-term impact risk assessments. Another area expected to benefit enormously is the study of variable stars. Unlike our relatively stable sun, many stars naturally brighten and dim over regular cycles, while others change unpredictably because of explosions, stellar interactions, or internal physical processes. Repeated observations over many years allow astronomers to follow these changes continuously instead of catching isolated moments separated by months or even years. Those long-term records help researchers better understand how stars evolve, how they die, and how they influence the environment surrounding them. Rubin will also become one of humanity's fastest discovery systems for explosive cosmic events. When a distant star suddenly goes supernova, or when two dense objects collide, the observatory's automated software can identify the change almost immediately. So while Rubin's first images captured headlines because of their extraordinary beauty and astonishing scale, they're really only the opening chapter of a much larger scientific story. The observatory has barely begun its planned mission. Years of continuous observations still lie ahead, along with billions of galaxies waiting to be catalogued, millions of moving objects waiting to be tracked, and countless changing phenomena waiting to be detected. If Rubin performs as expected throughout its full survey, future generations may look back on these first images not as the observatory's greatest achievement, but simply as the moment humanity first switched on one of the most ambitious scientific instruments ever built and started watching the universe in motion. If you want to keep following what Rubin uncovers as its full 10-year survey continues, subscribe and turn on notifications. The real universe keeps turning out to be remarkable enough on its own.